Hey, welcome back to Combinatorics. In this video, we're going to continue discussing induction. In particular, we're going to focus on weak induction. We started talking about weak induction in the last video, and we applied it to simplify some sums of some sequences of natural numbers. We initially started discussing weak induction because we wanted to use it to prove the inclusion-exclusion principle in full generality. So we saw the inclusion-exclusion principle for 2 or for 3 sets in a previous video. To recap, when we have 2 sets, A and B, the inclusion-exclusion principle says that the cardinality of the union of A and B is equal to the sum of the cardinalities of A and B minus the cardinality of their intersection. If we have 3 sets, A, B, and C, the inclusion-exclusion principle says that the cardinality of their union is equal to the sum of their cardinalities minus the cardinality of A intersect B minus the cardinality of A intersect C minus the cardinality of B intersect C plus the cardinality of their intersection of all 3. And we proved both of these versions of the inclusion-exclusion principle. The versions for 2 and 3 sets, we proved those in a previous video, and we applied them to several problems involving groups of students in schools. So any problems where you can model them with sets, it may be useful to use the inclusion-exclusion principle if you're trying to find the size of certain groups in your problem. We didn't prove the inclusion-exclusion principle for any numbers of sets past 3, although if we wanted to prove it for 4 and 5, we could have followed a similar proof. It would have just gotten increasingly complex. To state the inclusion-exclusion principle in full generality, we can say that the cardinality of the union of any n finite sets, A1, A2 up to AN, is equal to the sum over non-empty subsets S of the integers 1, 2 up to n of -1 to the cardinality of S minus 1 times the cardinality of the intersection over all J and S of the AJs. Notice that this fits the pattern that we see for the 2-set and 3-set inclusion-exclusion principle. So we have a sum of cardinalities of intersections with increasingly more sets in them. And as we increase the number of sets in the intersections, the sign changes in the sum. So we have an alternating sum. And that's why we have -1 raised to the cardinality of the set -1. So we're going to prove this fully general version of the inclusion-exclusion principle. And we're going to use weak induction like we used on the problems in the last video. Before we use weak induction to prove the inclusion-exclusion principle in full generality, let's recap what weak induction is. So we'll assume that P is any property of the natural numbers. For example, P of n could be the proposition that n is divisible by 1. Weak induction consists of multiple axioms of arithmetic. For each such proposition P, we can write a weak induction axiom. Now, when we apply weak induction, we can apply it starting from 0, or we can apply it starting from some positive integer. Typically, it's written starting from 0, but for many of the problems where we'll apply weak induction, we'll start from some positive integer, and we'll prove that our proposition is true for all positive integers, at least our starting spot. So the way to write that is to say that if we can prove that P of k is true, for some non-negative integer k, and we can prove for all n greater than or equal to k that p of n implies p of n plus 1, then we can conclude for all n greater than or equal to k that p of n is true. The first part of that, the p of k, is our base case. The second part, the for all n greater than or equal to k, p of n implies p of n plus 1, that's our inductive step. And what we're trying to prove is that for all n greater than or equal to k, p of n is true. So if we want to prove that, all we have to do is prove a base case and an inductive step. For the problem that we're looking at, for the inclusion-exclusion principle, the proposition p of n can just be defined as the statement that for any finite sets a1, a2 up to an, the cardinality of the union of the AIs is equal to the sum over non-empty subsets S of 1, 2 up to n of -1 to the cardinality of S minus 1 times the cardinality of the intersection over all J and S of the AJs. Since we're using weak induction, we're going to prove a base case and an inductive step. We're also going to use the two-set inclusion-exclusion principle in our proof. And that's fine to use because we already proved it in a previous video. So anything we previously proved is fair to use in future proofs. As a reminder, the two-set inclusion-exclusion principle just says that for any two sets, A and B, we have the cardinality of A union B equals the cardinality of A plus the cardinality of B minus the cardinality of A intersect B. So at the top of the slide is what we are trying to prove. We're trying to prove for any finite sets, A1, A2 up to AN, that the cardinality of their union is equal to the sum over the non-empty subsets S of 1, 2 up to n of -1 to the cardinality of S minus 1 times the cardinality of the intersection over all J and S of the AJs. So since we're using weak induction, we just start with a base case. We have multiple choices for our base case because we already proved the inclusion-exclusion principle for n equals 2 and n equals 3. And it's clearly true for n equals 1. So we'll take our base case as n equals 3. For the inductive step, we'll suppose that we have proved the inclusion-exclusion principle for n equals k. And we're going to use that to prove the inclusion-exclusion principle for n equals k plus 1. So our inductive hypothesis is that the inclusion-exclusion principle is true for n equals k. In other words, we can say that for any finite sets a1, a2 up to ak, the cardinality of the union of the AIs is equal to the sum over the non-empty subsets S of 1, 2 up to k of -1 to the cardinality of S minus 1 times the cardinality over all J and S of the AJs. That's our inductive hypothesis. And we want to use that inductive hypothesis to prove the next step of our induction, which looks almost the same as our inductive hypothesis, but we have replaced each of the k's with k plus 1s. So how can we prove that? Well, we can start with the left side of the equation that we're trying to prove. So we can look at the cardinality of the union of the AIs for I equals 1 to k plus 1. We can rewrite the union inside the cardinality as the union from I equals 1 to k of AI and union that with A of k plus 1. Here's where the two-set inclusion-exclusion principle comes in. It's because we've written that union as a union of two things. So the first set will be the union from I equals 1 to k of AI, and the second set will be A of k plus 1. So we can say that that cardinality is equal to the cardinality of the union from I equals 1 to k of ai plus the cardinality of a of k plus 1, and then minus the cardinality of the intersection of a of k plus 1 with the union from I equals 1 to k of ai. And all we used to get that was the two-set inclusion-exclusion principle, which we already proved was true in the previous video. So I've written that last bullet from the previous slide at the top of this slide so we can continue using it. So no new steps were done here. This is just a copy of that previous bullet. So we can take the right side of the equation, the cardinality of the union from I equals 1 to k of ai plus the cardinality of a of k plus 1 minus the cardinality of the intersection of a of k plus 1 with the union from y equals 1 to k of ai. Now what we'll do here is we'll replace the cardinality of that first union from I equals 1 to k of ai with a sum using the inductive hypothesis. And that sum is the sum over the non-empty subsets S of 1, 2 up to k of -1 to the cardinality of S minus 1 times the cardinality of the intersection over J and S of the AJs. We don't change the term that's the cardinality of A of k plus 1, but we do change the last term. So that last term where we have the intersection of A of k plus 1 with the union from I equals 1 to k of ai, we can rewrite that just as the union from I equals 1 to k of a bunch of intersections. And these intersections we write as ai intersect A of k plus 1. So we just distributed that A of k plus 1 into each of the terms in the union. Now, we can take the right side of that last equation and we can do another step. So we do not change the sum on the left. We do not change the cardinality of A of k plus 1 term. What we do change is the last term. And there we use our inductive hypothesis again, because again we have k finite sets that we're taking the union of. And that gives us the sum over non-empty subsets S of 1, 2 up to k of -1 to the cardinality of S minus 1 times the cardinality of the intersection over all J and S of AJ intersect AK plus 1. Now we can continue trying to simplify this in a way to get it to the other side of the inclusion-exclusion principle equation. And we again do not change the first sum. So we leave that first sum as is. We also do not change the term, the cardinality of A of k plus 1. The last sum though, we can change this one. So this one, instead of writing each of those intersections as the intersection over J and S of AJ intersect AK plus 1, we can just write them as the intersection over J in S union K plus 1 of AJ. And that's the only change we made from that bullet to the previous bullet. And again, I'm writing that last bullet from the previous slide at the top of this slide. I didn't make any changes. It's just so we have more space to finish off the calculations. So we can see that the equality here in the next bullet holds because the first term we didn't change at all. The A of k plus 1 cardinality term, we did change it this time. So we rewrote our last two terms and combined them into one term. So notice that the sum in the last term in the first bullet, that sum was over non-empty subsets S. But now I've changed the last sum in the second bullet so it's over any subsets S. They're not necessarily non-empty. So we're including the case when S can be the empty set. And when S is the empty set, then our intersection is over elements J that are elements of just the set K plus 1. So that's what gives us the term, which is the cardinality of A of k plus 1. So we just absorb that term into the sum. You'll notice also that in front of the sum, instead of a minus, we now have a plus. The reason why we got a plus there is because we changed the minus 1 to the cardinality of s minus 1 to a minus 1 to the cardinality of s. So we lost the power of minus 1, and that's why we changed a minus to a plus. Now we're almost to the end of the proof. We can simplify a little more. So we can still keep the first sum exactly the same, but the second sum, we can rewrite that a little. And we can say, instead of the sum over any s from 1, 2 up to k of negative 1 to the cardinality of s times the cardinality of this intersection over j in s union k plus 1 of aj, we're going to write s as a subset of 1, 2 up to k plus 1 instead of as a subset of 1, 2 up to k. We'll also require that k plus 1 is an element of S. So we're taking what we were previously considering the subsets S, and we're now renaming them so that S includes the k plus 1. And we still have the minus 1 to the cardinality of S minus 1 term, and we're multiplying that now by the cardinality of the intersection over J and S of AJ. So we've changed the J and S part. The J and S used to be J and S union K plus 1. And now since we've rewritten the indices for that second sum, we've included the K plus 1 in S already. So we do not need to union S with K plus 1 to include it in J. And finally, at the end, we can just combine these two sums together. We can note that the subsets S in both of these sums are non-empty. So the first sum says that S is not the empty set. So that's why those S's are non-empty. And the second sum, it says that K plus 1 is an element of S. So those S's are also non-empty because they must contain the element K plus 1. We can also see that the S in both of these sums has no overlap. So the S subsets in the first sum do not contain K plus 1. The S sums in the second sum must contain K plus 1, and all of these S are non-empty. So we have a sum over non-empty subsets S of 1, 2 up to K plus 1 of negative 1 to the cardinality of S minus 1 times the cardinality of the intersection over all J and S of AJ. And that completes the proof. That completes our weak induction. So we just proved the inclusion-exclusion principle in full generality for any number of finite sets. And that's our statement that we have. So we proved that that is true. So the union of the AIs, if you take its cardinality, it's going to be equal to this alternating sum. So in the previous video, we saw a lot of example problems where we applied the inclusion-exclusion principle to figure out how many students are on various teams in a high school. And other problems like that can also be solved with the inclusion-exclusion principle. For example, we saw some problems about the probability of getting certain hands in poker. What's the probability of getting this card or that card, or this card or that card or another card? So we can have multiple ors. We can have 4 things in our disjunction. So here's a problem for you to think about. Maybe the inclusion-exclusion principle could be useful for it, or maybe something else would be better. Here's the problem. Find the probability of being dealt a hand with at least 1 queen, or at least 1 diamond, or at least 1 ace, or at least 1 spade in Texas Hold'em poker. Before we finish this video, let's look at another example of a proof that we can do with weak induction. This is a different kind of problem that we haven't seen yet, but it's something that is going to be very straightforward with induction. and it'll follow the same pattern of the induction proofs that we've seen. The problem is to prove that for every natural number n, the number 9 to the n minus 2 to the n is divisible by 7. Since we're proving this with weak induction, we will prove a base case and then we'll prove an inductive step. The base case will be n equals 0. We can see that 9 to the 0 minus 2 to the 0 equals 1 minus 1, and that's equal to 0. And 0 is divisible by any positive integer, so it is divisible by 7. For the inductive step, we'll suppose that 9 to the k minus 2 to the k is divisible by 7 for some natural number k. We want to prove that 9 to the k plus 1 minus 2 to the k plus 1 is also divisible by 7. We can write 9 to the k plus 1 minus 2 to the k plus 1 as 9 to the k plus 1 minus 2 times 9 to the k plus 2 times 9 to the k minus 2 to the k plus 1. All we did here is we introduced a new term and then we canceled it out. The new term was minus 2 times 9 to the k, but then we added a plus 2 times 9 to the k to cancel it out. So we didn't change anything, but this is going to be useful to us for writing things in terms of multiples of 7. So we take the first two terms we have, the 9 to the k plus 1 and the minus 2 times 9 to the k. That gives us 9 to the k times 9 minus 2 when we factor out the 9 to the k. We take the last two terms, the 2 times 9 to the k minus 2 to the k plus 1. We can write that as 2 times the quantity 9 to the k minus 2 to the k. So we can simplify a little and write this as 7 times 9 to the k plus 2 times the quantity 9 to the k minus 2 to the k. We know clearly that 7 times 9 to the k is divisible by 7. So we need to check the other part of it, the 2 times 9 to the k minus 2 to the k. However, we can use our inductive hypothesis there. Our inductive hypothesis was that 9 to the k minus 2 to the k, 9 to the k minus 2 to the k is divisible by 7. So that tells us that 7 times 9 to the k plus 2 times 9 to the k minus 2 to the k must also be divisible by 7. And since that's equal to 9 to the k plus 1 minus 2 to the k plus 1, we can conclude that 9 to the k plus 1 minus 2 to the k plus 1 is divisible by 7. That completes our induction proof for that problem. So here's a problem for you to think about that's kind of similar. Prove or disprove that 54 to the n plus 24 to the n minus 23 to the n minus 13 to the n plus 12 to the n minus 10 to the n is divisible by 11 for every natural number n. That brings us to the end of this video. Thanks for watching.